Welcome to lecture series. In my previous classes, I have discussed about the concept of basis, linear independence and dimension. So, let me continue with that. I have shown that if V is a vector space and if it is a finite dimensional and if it is spanned by say finite number of elements, say beta 1, beta 2, beta m, then the number of element of that linear independent subset will be less than equal to m please. I mean it cannot exceed m please. So, there is another small results based on that principle only I will say it. Suppose S be a linearly independent subset of a vector space over F. Suppose beta is an element of V which is not in the linear span of capital S. Then by adding beta to capital S will be again a linearly independent subset of V please. So, let me give the proof. Let S consist of n elements say alpha 1, alpha 2, alpha n. So, these are all distinct elements. Consider A star is equal to beta alpha 1, alpha 2, alpha n. It is given to me beta is not in the linear span of capital S. Now, my claim is that A star is a linearly independent subset of B. Suppose not. Suppose A star is not a linearly independent subset of B please. So, this means that there exist n plus 1 scalars say A naught, A1, A2, An belongs to capital F such that A naught beta plus A1 alpha plus A2 alpha 2 plus An alpha n is equal to 0. Here A naught not equal to 0, otherwise beta is not coming to the pictures and we know that alpha 1 to alpha n is a linearly independent. So, therefore, I have considered A naught not equal to 0. So, this implies that beta can be written as minus A1 by A naught into alpha 1 plus minus A2 by A naught into alpha 2 plus minus An by A naught into alpha n. So, this implies beta belongs to linear span of capital S, which contradicts the given condition. So, S star is a linearly independent subset of capital V. Now, this concept will help us from a linearly independent subset of a vector space, one can extend this linearly independent subset of the vector space to be basis of the corresponding space. So, it is something called the extension theorems. So, this we can easily prove by adding one by one elements and so this is I am giving as homework please. So, that I am saying of course it is a extension theorems. What is extension theorems? Suppose V be a finite dimensional vector space over the field say capital F, and S be a linearly independent subset of V, then that subset can be extended to be basis of the corresponding space V also. So, this I am leaving as a homework please. Now, let me consider another interesting subset or subspace that is basically come as a part of the sum of subspaces what we introduced in last classes please. Now, it is like this, if W1 and W2 are finite dimensional subspaces of a vector space V over capital F, then dimension of W1 plus dimension of W2 equal to dimension of W1 intersection W2 plus dimension of W1 plus W2. Before proving these results, let me quickly give in a geometrical picture so that one can have idea how to proceed to prove this one please. So, what I will do, let me take our V is equal to as R3 please. Now, let me consider here say W1 is equal to, this is my x, y, z. So, W1 is xy plane and W2 is x axis. We know both of them are subspaces. Now, if I consider W1 plus W2, the sum of subspace W1 and W2, this will give me what? It will give me simply xy plane. So, dimension of W1 plus W2 will be equal to basically 2, and dimension of W1 is equal to again 2, dimension of W2 is equal to 1. What about W1 intersection W2? W1 intersection W2 is basically x axis and dimension of x axis is again 1. So, you see that dimension of W1 in this example is equal to 2, dimension of W2 example 1. So, 2 plus 1 equal to 3, and if I see that right hand side dimension of W1 intersection W2, that is equal to 1, and plus dimension of W1 plus W2 is again 2, because W1 plus W2 is nothing my xy plane, that is W1 only. So, therefore, I see that this relation holds good please. So, now let me give it more generalized form please. Since W1 and W2 are finite dimensional subspaces of V. So, W1 intersection W2 is also a finite dimensional subspace of V please. Let B equal to alpha 1, alpha 2, alpha k be a basis of W1 intersection W2 please. We see that B is basically subset of W1 intersection W2 and linear span of B is equal to W1 intersection W2, and W1 intersection W2 is a subset of W1 and it is also subset of W2. So, by extension theorems I can extend the B to B1 to be basis of the W1. So, let B1 which is equal to alpha 1, alpha 2, alpha k and beta 1, beta 2, beta m be a basis of W1 and B2 consisting of alpha 1, alpha 2, alpha k and gamma 1, gamma 2, gamma n be a basis of W2. Claim B star which is equal to alpha 1, alpha 2, alpha k, beta 1, beta 2, beta m, gamma 1, gamma 2, gamma n. Claim this is a basis of sum of subspaces W1 and W2, that is W equal to W1 plus W2 please. So, first I have to show that B star span W, and second I have to prove that B star is linearly independent. So, first is B star spans W which is equal to W1 plus W2. Okay. Now, to prove that one, what I have to do? We know any element W belongs to capital W can be written as W is equal to something like W1 plus W2, where W1 belongs to capital W1 and small w2 belongs to capital W2. Okay. So, since W1 belongs to capital 1, so I can write down the small w1 as a linear combination of the basis element of W1. So, there exist scalars C1, C2, Ck and D1, D2, Dm such that W1 equal to, I can write down sigma Ci alpha I equal to 1 to k plus sigma Di and beta I equal to 1 to m. Okay. So, this Ci and Di belongs to corresponding field place. Similarly, one can have linear combination of like this, suppose this is equal to Fi alpha I equal to 1 to k plus suppose this is equal to say Gi your gamma I, okay, I can write Gr gamma r equal to say 1 to n like this. So, W is equal to W1 plus W2 is nothing, I will have sigma Ci plus Fi into alpha I plus I equal to 1 to k plus sigma Di beta I equal to 1 to m plus sigma your G r and gamma r equal to 1 to n. So, this means that W can be written as linear combination of alpha I, beta I and gamma I also. So, this implies that W belongs to the, I can say, LS of B star, or the B star spans capital B. Now, claim is that B star is also linearly independent. B star is linearly independent. I have to prove that one. I will prove it by contradiction. Suppose it is not linearly independent. Suppose B star is not linearly independent. So, it is linearly dependent. So, there exist scalars say C1 to Ck and D1 to Dm and G1 to say Gn such that your sigma Ci alpha I equal to 1 to k plus sigma Di beta I equal to 1 to say m plus I can say G r and gamma r are equal to say 1 to n, this is equal to 0, where not all Ci or di or gamma gi are equal to 0 please. So, this implies that one can write down sigma Ci alpha I plus sigma di beta I equal to sigma minus g r into gamma r equal to 1 to n, I equal to 1 to say m and I equal to 1 to k please. So, this implies sigma minus g r gamma r equal to 1 to n belongs to W 1, but we know sigma minus g r and gamma r are equal to 1 to n belongs to W 2, because gamma 1, gamma 2, gamma n is basically part of the basis element of W 2. So, this implies what? Sigma minus g r gamma r are equal to 1 to n belongs to W 1 intersection W 2. So, this belongs to this quantity. So, this means that I will be able to express this element as a linear combination of the basis element of W 1 intersection W 2. So, this implies there exist P 1, P 2, P k such that sigma P I alpha I equal to 1 to k equal to minus g r and gamma r are equal to 1 to n. So, this implies I can say sigma P I alpha I equal to 1 to k plus sigma g r gamma r are equal to 1 to n equal to 0. Since alpha 1 to alpha k and gamma 1 to gamma n is a linearly independent subset of V. So, each G I 0 for r equal to 1 to n. Of course, P I also equal to 0, I equal to 1 to k also, 1 to k. So, if I use that G r equal to 0 for r equal to 1 to n in my expressions that where I have considered the linearly dependent, so these relations in star. So, star implies sigma C I alpha I equal to 1 to k plus sigma d I beta I equal to 1 to m will be equal to 0. So, this implies again, since alpha 1 to alpha k and your beta 1 to beta m is a linearly independent set. So, this implies that C I equal to 0 and d I equal to 0 or I equal to, okay, I can say this one j equal to 1 to m. So, that will be not to confuse, okay, for I equal to 1 to k and j equal to 1 to m, which contradicts our hypothesis that at least one coefficient not equal to 0. So, this star is linearly independent. So, this implies that dimension of k plus m plus n. So, this implies dimension of W1 plus W2 equal to dimension of W1 plus dimension of W2. Okay. So, I can write down this is again plus k and minus k. Okay. So, dimension W2 minus dimension of W1 intersection W2 please. So, this is the results that if W1, W2 are two finite dimensional subspaces of a vector space V, then dimension of W1 plus W2 equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. See, so far what we have discussed here, we have considered linearly independent or dependent of set, but we have not considered the linearly independent or dependent of some finite sequence of vectors. We need this sequence concept to understand more deeper sense of the vector space and its applications. So, I will introduce one terminology called order basis. Order basis. Let V be a finite dimensional vector space over capital F. A subset B of V is said to be an order basis of V provided one V is a basis of V and second B is a order set. I mean to say it follow a patterns, I mean some order is there please, the order set. So, let me take examples. Now, let me consider, let V is equal to say F3. Suppose V is equal to say alpha 1, alpha 2, alpha 3 is a basis and B star as alpha 1, alpha 2, alpha 3 is an order basis. So, what is the difference between this? See, in this first B, it is a basis fine, but there is no order whether alpha 1 will be first element, alpha 2 will be second element, is it like that? No, there is no. See here this B is basically same, I can write this is also equal to alpha 2, alpha 1, alpha 3. But in the case of order basis, here the first element is fixed, the alpha 1 is the first element, alpha 2 is the second element and alpha 3 is the third element please. So, here order is preserved. Okay. So, let me see what sort of benefit we will see by introducing this concept. Consider V be a finite dimensional vector space over capital F. Let B equal to alpha 1, alpha 2, alpha n is an order basis. Okay, Bn be an order basis please, order basis of Now, for any alpha belongs to V, there exist n scalars C1, C2, Cn such that alpha equal to C1 alpha 1 plus C2 alpha 2 plus Cn alpha n. So, this implies it introduced an n tuple scalar please, that is C1, C2, Cn. So, this belongs to Fn. So, this implies for each alpha belongs to V, there exists a n tuple, so C1, C2, Cn belongs to Fn. Is it possible that one can have another n tuples which is also express alpha? Let me see. If alpha also equal to say x1 alpha 1 plus x2 alpha 2 plus xn alpha n, this implies that I will have C1 minus x1 into alpha 1 plus C2 minus x2 into alpha 2 plus Cn minus xn alpha n equal to 0. This implies Ci minus xi equal to 0 for I equal to 1 to n. Since alpha 1, alpha 2, this is a linearly independent set of V. So, this representation is also unique please. And another interesting fact, you see, if I pick beta belongs to V and beta is equal to say, let us consider something like y I and alpha I equal to 1 to n, then alpha plus beta is equal to, I can simply say that xi plus yi alpha I. So, this xi what I am writing here for the alpha is equal to like this, is introducing the coordinate ith coordinate please. So, okay. So, here this Ci is ith coordinate. So, there exists an 1-1 relation between the n dimensional vector space V to f n alpha goes to something like C1, C2, this n tuple Cn please. Now, we want to see what is the benefit by introducing this concept please. Let V be a again be a finite dimensional vector space over a field say capital F. Let B equal to alpha 1, alpha 2, alpha n be an order basis. Let for alpha belongs to V, there exists an n tuple say x1, x2, xn such that your alpha equal to sigma xi alpha I, xi belongs to capital F. Then capital X equal to x1, x2, xn transpose is called as coordinate matrix of alpha with respect to order basis B. So, the transpose of x1, x2, xn, that coefficients, is called the coordinate matrix of alpha with respect to B. Symbolically, I can write that coordinate matrix of alpha with respect to order basis B is equal to here x1, x2, xn transpose, which is equal to capital X place. So, this one belongs to F n cross 1 column vector place. So, this implies for each alpha belongs to V, there exists a coordinate matrix, say alpha like this thing. There is a one-to-one map between the set of elements of capital V and space of n tuples place. So, if you consider any n tuples, say x1, x2, xn belongs to Fn, we have seen that the sigma xi alpha I will be element of capital V. Now, this x1, x2, xn transpose, I am saying that as a coordinate matrix. So, I can say that for each alpha there exists a coordinate matrix. So, it is a one-to-one relation holds good place. Now, we are curious to see if I change the basis, if I take the, so there are two bases B1 and B2, then how the coordinate matrices are related, or if at all there is a relation or not. Before that, let me take an example of how to find the coordinate matrix of a vector. So, let V equal to F3 place. Let B equal to 1 1 1 1 1 0 1 0 0. We can immediately check this B is a basis for the space V please. Let me consider this B is also an order basis, is an order basis of V please. Okay, let alpha equal to ABC belongs to F3 be any element. Then we want to know what about the coordinate matrix of alpha with respect to this order basis B. So, here my first element is this one, second is this one, third is this one please. So, I have to write down A, B, C as a linear combination of G1 1 1 1 plus G2 1 1 0 plus G3 1 0 0. So, I have to find what is this coefficient G1, G2, G3, whose transpose will be basically my coordinate matrix of alpha. So, this is equal to G1 plus G2 plus G3 comma G1 plus G2 and then this is G1 please. Okay. So, this implies G1 equal to C and G1 plus G2 equal to B implies that G2 is equal to B minus C and we have G1 plus G2 plus G3 equal to A. So, this implies that G3 is equal to A minus B. So, coordinate matrix of alpha with respect to B will be C, B minus C and A minus B, this transpose. Okay. So, it is like this thing please. Okay. So, now let me pose a questions. Let V be a finite dimensional vector space of dimension say n. Let B equal to alpha 1, alpha 2, alpha n, and B prime equal to alpha 1 prime, alpha 2 prime, alpha n prime. Be any two order basis of privilege. Let alpha belongs to V be any element, be any element. Let coordinate matrix of alpha with respect to B is equal to capital X, and coordinate matrix of alpha with respect to B prime is equal to capital X prime. I mean x equal to x1, x2, xn transpose, and x prime equal to x1 prime, x2 prime, and xn prime transpose, please. Now, we want to know, is there any relation between capital X and capital X prime? That is the question, please. Answer is yes. What is that relation, please? There exists an invertible matrix P of n cross n order such that capital X is equal to P into capital X prime. So, now we have to prove for these relations. I will do in the next class. So, I hope you have understood the part which we have covered in this class. So, based on this I will continue in the next class, please. Thank you.